This is the fourth and final video for the lecture for September 4th, and we are going to look at the beginning of 3.3. The plan is to finish 3.3 in class on Tuesday. So if we just look at this linear function, which is in the form y equals mx plus b, this is a very simple question, but might look a little confusing because it asks for the rate of change in addition to the slope and y-intercept. And so to introduce this concept, I want to look briefly at the textbook. The average rate of change of a function is the same thing as the slope. So as you can see, the slope formula y2 minus y1 over x2 minus x1 is the same formula that's used for average rate of change. And it can be expressed in any one of these formats. This format is used when you have a function instead of y. This format, delta y over delta x, is just used to express change in output over change in input. So in this case, the rate of change is -7 because the slope is -7. So they are going to be the same thing. And the y-intercept is going to be 0, 5, expressed as a point. Okay, so I did add the average rate of change formula for you here. When you're looking at this table, what you're going to be doing is looking at a change in input and change of output. The input is years, the output is sales. So we would set up the average rate of change as follows. The average rate of change is equal to the change in sales over the change in years. This triangle is the Greek letter delta, and in math it represents a change of. So for the sales between 2020 and 2024, which would be your change in years, placed here, we have the sales of 316 and 356. So you want to make sure the 316 corresponds with the 2024, so it needs to be listed first. And then 356 will be listed second because it corresponds to 2020. Okay, and so what that simplifies to is -10, because you have -40 divided by +4, which is -10, and the units that are included here are millions of dollars per year. Now, average rate of change is also expressed for a function using this formula here, and we can do that two different ways for number 3. I want to show you both ways so you can understand the concept. Let's start by using the formula. So noting that this red point on the left is the origin, 0, 0, and on the right we have 4, 4. We can do 4 minus 0, 4 minus 0, and it turns out that the average rate of change from one red dot to the next is simply 1. Now that makes sense for a slope if you have a line, but here we have a squiggle. So what's going on here? So what the case is that if you were to connect a line going from one red dot to the next red dot, this yellow line here is going to have a slope of 1 because it goes through 0, 0 and 4, 4. The blue line that's going up and about is going to have an average rate of change of 1. So the reason the average rate of change is slightly different from slope is that it represents over the course of a curve moving at many different rates of change, sometimes negative, sometimes positive, sometimes in a very steep manner, sometimes in a not as steep manner. Over the course of the entire interval, 0 to 4, if you were to take an average of all of these rates of change, it could be computed by way of looking at the slope of the line connecting the beginning to the end. And so that is really what differentiates slope and rate of change. Now, when you have a linear function, as in the case of number 1, the linear function is always going to have a rate of change that is equal to the slope because it is the same thing for a single line. But when you have a curve, the average rate of change is computed by finding the line And the slope of the line then ends up becoming equal to the average over the course of the entire curve. And the concept is like if you're traveling and you are going a certain miles per hour as you're traveling, and sometimes you go faster and sometimes you go slower, but in the end you can find out what your average speed was for the entire journey by figuring out how far you went and how long it took you, even though sometimes you might have been stopped, and even though sometimes you might have been going 70 miles per hour, you might find that on average you were going about 50 miles per hour as you compute the distance divided by the time. Okay, in the case of number 4, we can use the coordinates, but alternatively the fast way to do this is just to find the line. So if you can find the line connecting the 2 points, you can observe that the change vertically is 2, and the change horizontally is also 2, and so that is going to give you a 2 over 2, so the slope here again is 1. In the case of a curve such as this, we wouldn't be able to just count boxes. So yes, you could have a line drawn, and that line can be visually helpful for you, but at the end of the day, you're still going to just need to use the computation for slope using these points. And so what we end up with is 43.84 minus 26.14 represents the change in y, and the change in x is 8 minus 2. That simplifies to 17.7 over 6, or 2.95, which you can see is the answer here. An interpretation for this problem would be that the fuel consumption increased because 2.95 is a positive amount. That should be pretty straightforward. Okay, so in the case of number 6, it's asking us to mark two different points here on the graph. We're going to connect the points with a line segment. And we're going to do that. We've got the dot and the line segment feature here. We want one point at -7. So if we find -7 and trace -7 up, we find that we have a dot at -7, 8. And then the second point is got to be at -4. So we find -4 and we trace it down to the point where it's located. And now we connect with a line segment from -7 to -4. And then the result is the average rate of change across the red in this interval will be represented by the slope of this line. So the slope of this line you can find counting boxes. You go down 3 over 1, down 3 over 1, down 3 over 1, and that's why we see that the average rate of change is -3. Question number 7 is going to be the same thing. And when you're drawing these line segments, you can clear it each time. It just gives you the option to draw it and then erase it, draw it and then erase it to come up with your answers. So let's look at 0, 2. So at 0, my graph is going to start here, and at 2, it's going to go down to this location, and then I can look at that blue and see that the slope of that blue segment is -2, and so that's what I would type in here. And then I can clear that and try again from 1 to 2. So at 1, my graph is located at 1, 5, and then to 2 is now 2, 4, and the slope of that line is -1. Then I can clear again and do 3, 4. So at 3, I have a dot here, and at 4, I have a dot here, and then I can see that the slope of that line segment is 3. So you don't have to leave each of these dots on here. It just says feel free to draw in the line segment for each interval if that's helpful. Okay. Question 8. The graph P of t below shows the population in thousands of people of a city t years after 2008. So it's easier for us to look at the big graph, but you can see that the population is in thousands, so this would represent 3,000. And the years are time after 2008, so for instance, 5 would be 2013. Note that 8 years after 2008, the population is approximately 5.98, and 16 years after 2008, the population is approximately 11.91 thousand people. And that's important because as you're trying to figure out these average rate of changes, you need these exact numbers. So we need to find the average rate of change to 2 decimal places from 0 to 8 years, from 8 to 16 years, and from 0 to 16 years. So what you'd want to do is do this algebraically. So we'll start with 0 to 8 years. We're looking at finding the slope of this line right here. And so we'll use the slope formula. And we know that this point here at 8 is 8 years after, has a y value of 5.98, and here at 0 we have a y value of 3. So then to find this ratio, you would want to put that in the calculator. You have 2.98 divided by 8, and my calculator is not popping up on the screen right now for some reason. So calculating the quotient, we get 0.3725. We're supposed to round to 2 decimal places, so that would be 0.37. And the other thing we need to do is select the units, and this would be population per year, so that would be in thousands of people per year, and that's the correct answer there. And we can see that indeed that was the correct answer. The process for 8 years to 16 years is going to be the same. You're going to look at the slope from 18 to 16. Be sure to use the exact numbers that are listed in the description, and 0 to 16 will be the same as well. And what you'll find is that 0 to 8 had a slow growth, 8 to 16 had a fast growth, and that if we average over the course of 0 to 16, we're going to end up with something in between. From each of these, you would also then go on to answer the questions here about the meaning of the rate of change in this context. And so we can see that the city's population is growing. Is it growing at a consistent rate? Well, no. At first it's growing slowly, and then it's growing faster. So we would say it is increasing at an inconsistent rate. And then it says, what do the values above tell you about the rate of change of v of t? If you have an inconsistent rate, it would be nonlinear. Now, what's going on with this v of t and d of t? Well, this is clearly some sort of error from the person who coded this. Both of these should be p of t. I'm not sure if I can figure out how to change the code on that, but I will look into that. And in any case, just what you want to recognize here is that an inconsistent rate is going to be nonlinear, because a line is going to give you a constant rate the whole time. A line has a constant rate of change. But anything that's not a line, whether it be a squiggle or a smooth curve, these are going to be nonlinear and therefore inconsistent. So after this, we're going to get to some more difficult problems that I would like to do in class. So I'm going to pick up with number 9 in class. 9 through 12 will actually be required for the work that you hand in, but the other problems will not be. So then this is the last video for the lecture for Thursday, September the 4th.